Hi, everyone. Okay, let's get started. Yeah, so before we start, there's an announcement. First one, today we do not have extra session. Yeah, also yesterday we don't have extra session. Sorry about the confusion. Yeah, so we don't have exercise today. And second, I think the original link I put on the website has some problem. I just fix it. Try again. If there's any problem, just let me know. Okay. Yeah, so another thing, today is the last day of the semester, right? So we'll do what what we have been doing last year. That is during the summertime when you study the material of this course, right? So you might have problems, you might have questions. We have 4 additional office hours after today, right? So during the summer break before your exam. This is the date and this is the time. If none of this work for you, you can always send me an email, but I think in expectation, you could just take 1 or 2 of these slots and use the same Zoom link. So I'll be there to answer the question. We will record the office hour to make sure I can upload it to YouTube, right? So, and then everyone, whoever want to, like to make sure everyone has the same information, right? So someone raise hand, go ahead.
Yes, Professor. Again, because of the slides, for me, it still says if I click on the link, this item might not exist or is no longer available.
Oh.
It doesn't seem to work. It also confirms all of, or also the slide from Wednesday is also not available anymore. There seems to be a permission issue.
Oh, can you give me a minute? Yeah, so
Sure.
let me try to see what happened. Huh. But all the other slides you guys can access, right? Without any problem.
I'll just check.
Huh.
No, they don't seem to work anymore.
Okay, yeah. So yeah, okay. So I think there's some problem with my OneDrive. I don't know. Yeah. So
someone just shared another link that works. I don't know why, but it looks fine.
Okay, I will definitely fix it. Probably not right now. Yeah. Sorry about this. Yeah, I think there's some problem with OneDrive. I think all the slides now is broken. All the links are broken. Okay, yeah. So I will for sure fix it after the course. Okay. Yeah, sorry about that. Yeah, okay. So yeah, so we have this like 4 office hours, right? You can just call in, right? We'll record it and we'll put essentially all the question answering also on YouTube, and then everyone can just look at it. Okay. I don't think you need more, right? So, but if you need more, you can obviously send me an email, right? But otherwise, yeah, you can always, yeah. So call in, right? Yeah. Okay, great. So today, right? So we have been doing one of this session around Easter, right? So to really, I mean, go through what we have been learning, right? And introducing some structures about what we have, and also go through some exam questions, right? So the goal is really to try to calibrate expectation because there are a lot of things in the book, right? We want to make sure at least we give you a well-defined scope, and then to make sure we really learn from it. Like we're kind of learning for database, you have the target, right? You have the scope, right? And then you can focus on what's important, right? So that's the goal, okay? So if you look at the structure of exam, right? So we actually talk about most of the questions before Easter, right? So essentially we talk about how to use database as a user and how to build one application. That's always the core of this course. So the thing that we talk about essentially after Easter, right? Actually, like couple of weeks after Easter, it's about systems, right? So how does the system work? how does, if you give a database a SQL query, how does the system answer the SQL query, right? And also on the other hand, if you have multiple of those SQL queries, how does the database deal with the correctness of the execution, right? How does that database deal with transactions? So there's a lot of content, right? But not too many questions in the exam, because when you talk about systems, it's sometimes it's very easy to actually test whether you understand the system, right? Because to reason about the end-to-end behavior of the system, you need to understand like the behavior of every single layer, right? So that's why we don't have 2 questions here, right? But it doesn't mean they're not important, right? So it's simply because when we talk about system, it's kind of easier to kind of test your understanding end-to-end with a single question, okay? So the principle is going to be similar to previous years, right? It will be online, like online in the sense that it will be on Moodle, right? And the format is mainly multiple choices, right? So now let's try to walk through the content of the second half of the course and try to define and calibrate our expectation, okay? So after Easter, right? So essentially we talk about 2 topics. In the first topic, we talk about essentially how does a textbook database system works. So let's try to simplify our assumption, right? Because a real world database management system can be pretty complex, right? We have shown this figure for multiple times, right? So if you go to Oracle to say, okay, I want to buy a database, right? So this is probably what they are going to give you every couple of years ago, right? So they are going to give you a whole rack, right? And multiple servers, right? For this one, it's like 0.5 terabyte of memory per server, right? And all those machines are connected by like 40 gigabits network, so on and so forth. And you have maybe almost 0.5 petabyte of storage, right? So in this whole rack. So that is what a kind of real world database looks like a couple years ago, right? If today you go to Oracle and buy a database, right? So I mean, even more beefy than this, right? So in this course, of course, we didn't talk about it, right? So we talk a little bit about distributed query processing, right? But not too deep. We will focus on relational database systems with a disk-oriented architecture with a very simplified assumptions. That is, all data are stored on secondary storage, here, hard drive. And we assume the hard drive is larger than memory, okay? So this may sound like a trivial assumption, but yeah, on a single server, you have 1.5 terabyte of memory, right? So we assume disk is larger than memory, okay? And we assume disk is slower than memory in different ways, okay? So the random access is slower, sequential access is slower, okay? So they have different consequences, right? But we assume disk is slower than memory. And this has different access pattern. So essentially we are kind of deal with the device that can only be addressable by blocks, okay? Like whenever you kind of read and write, you are dealing with a whole block of information. So that is why when you have sequential access, when you have random access, you have different performance for different access patterns. So that's our basic assumption, right? So essentially in this chunk of the material, I mean, we are going to take these assumptions and try to understand how to build a database systems. So let's kind of take this assumption on the architecture and on the hardware, right? Let's try to understand essentially a performance model, right? What operation can we do? What operation we cannot do, and why, and how can we model it? So given this cost model on the architecture, later, when you have different physical plans, right? So now I think everyone understands what that means. When you have different physical plans, you can reason about its performance. And then the query optimizer, right, can pick the best performance plan automatically for the user. And that's a holy grail. And that is our end goal of this. So to understand the performance model of the architecture, right? So essentially we try to make the previous assumptions a little bit more precise. So essentially we are dealing with the storage hierarchy, right? So that's actually one fundamental limitation for disk-oriented architecture. That is, you do not have an infinite amount of memory, but instead all your storage is organized into a hierarchical structure, right? On the top, you have your register, right? Maybe like roughly the size, maybe 1,000 kilobytes, something like that, right? Depending on your processor. Then you have your L1 cache, L2 cache, LLC cache, right? Then you have your main memory, you have your hard drive, right? So from the top to the bottom, right, it's getting larger and larger and cheaper, right? But on the other hand, it's also getting slower, okay? So how does hard drive works, right? So we need to understand this, otherwise we don't know how to model the performance. So hard drive works in a very simple way, right? So you have like a whole bunch of disks, right? And then you have the head, right? That can actually read essentially one sector or one chunk of sectors, right? On your hard drive. And the disk keeps spinning, right? Essentially, if you want to access the information at certain location on the disk, right? So it's very natural about what cost you need to pay, right? You need to rotate the disk, you need to rotate the head, right? Such that your disk head is at the right position, then you read, right? And then you transfer information. So there's always the latency and there's always the throughput, okay? Whenever you are accessing information. The latency here is the physical time that you need to rotate the disk and rotate the head, okay? And the throughput part is actually how fast you can move information from the disk to your main memory in this case, okay? So in the cost model, there's always two components. One is about latency, about rotation, another is about information transformation, okay? And we assume there's only one read and write at any time. Whenever I'm reading something, you are reading a block, okay? And the block is a multiple of the sector size. So given this, we can actually have a very simplified, actually not that simplified, I mean, kind of reasonably like accurate performance model, right? So you have the seek and rotate time, right? Which models essentially the time field to rotate the disk and also for the time field to rotate your head, okay? So, and then there's a transfer time, right? So how long does it take for you to transfer, for example, 1 megabyte of data or one whole block, okay? So, and whenever you have a random access, assume you have D random access, D different locations on your disk. So essentially I need to pay D times the seek time, rotate time, and transfer time. Why? Because every single time you access data, I need to rotate, I need to like rotate my disk, rotate my head to find like to put the head in the right location. And because it's random access, right? Every single time you access something, I need to redo that. Whenever you have sequential access, right? So because they all stored sequentially, right, on my disk, I only need to seek and rotate once to find the right position, and then I can keep transfer, okay? And then the head doesn't need to change. I just rotate my disk, right? But while I'm rotating my disk, I keep reading information. So essentially, the time that you need to rotate the disk is hidden from like it's hidden within the kind of transfer time, okay? So if you have sequential access D times, a simplified performance model would be you pay 1 unit of seek and rotate time, and then you pay D units of transfer time. So as you can see, the difference can be huge because the seek and rotate time is actually very large. The seek and rotate usually at a scale of kind of 10 to 20 milliseconds, and today it's a little bit faster. I mean, it's actually bounded by how fast the disk can physically rotate. And that is something that's kind of hard to improve over time, because I mean you can only rotate the disk that fast because there's a whole bunch of, when you rotate too fast, maybe the whole thing get too hot, right? So, and that is actually something that little bit hard to improve, okay? So even today, the seek and rotate, I'm sure it's faster than 10 to 20 milliseconds, but it's still at the millisecond level, okay? On the other hand, the transfer time, right, it's kind of easier to improve. Why? Because you can keep adding those disks, right? So the moment you kind of double the number of disks, right? So you kind of double your transfer bandwidth, then you kind of decrease this side, okay? It's very similar to how do you make a network faster, right? Well, like how do you make the bandwidth larger, right? You can keep adding those that kind of like to zero order approximation, right? You can like plug in another wire, right? Okay, so difference can be huge, right? So I mean, if you do the kind of back on the envelope calculation on how large, how slow it is to read 1008 kilobyte blocks, you can see there's kind of orders of magnitude difference here, right? So when we talk about database systems, given the behavior of the hard drive, given the memory hierarchy, right? The whole thing can become a little bit complex. This is 2 examples about what happened in real world. But in this course, we talk about a database system with multiple layers, okay? On the top, there's the layer dealing with SQL queries. It takes as input the SQL query, it output a relation. At the bottom layer, right, all of your information are stored in your file system. And then let's just go through that one by one. All of your things are stored on files. And then there's a disk manager, right? So what is, and then there's a buffer pool manager, there's a whole bunch of access methods, there's the implementation of different relational algebra operations, right? And then there's the query optimization part. So what does disk manager do, right? Let's just think about it. So all your information are already on your file systems. So the job of the disk manager, right, is really try to access the disk, interact with the disk, okay? So there are multiple things that we need to do, right? So we need to allocate the page, right? And we need to delete the page and then to fetch the page. And we'll design this part, right? You also need to understand, okay, then what is a page, right? How do I store the information? And we talk about 2 different ways for you to do that. If you do, for example, row store, right? So you can store the whole tuple together, right? And then we talk about how to do that. And we talk about the page layout, tuple layout, right? How can you organize a file, right? We talk about heap file. We talk about like 2 different implementation of that, right? Essentially the information format, right? How do you really store, like store your data? What's your data layout? That's one thing. If you do column store, right, so different data layout, right? And then given that layout, so the disk manager's job is to make sure whoever want to access information in your file does not deal with a file on their own. Instead, they talk to a disk manager to get access to the file. Allocate the page, delete the page, fetch pages, insert tuples, fetch tuples, given the record ID. Record ID is the pair between page ID and slot ID. Right? The goal is essentially other layers do not interact with disk. So here you need to deal with storage layout, right? So that's something that we talk about. And then one layer above that is the buffer pool manager, right? So the problem is that your hard drive is much larger than my memory, but I really want most of my database system, when I implement them, has a logic dealing with the memory side, because that's easier, right? Otherwise, I need to think about too many things. I want to provide one level of abstraction to get rid of the hard drive. And that is what happened in the buffer pool management side. So essentially, we keep in-memory buffer, and all the upper layer have the illusion that data is in memory, not on disk. Whenever they access information, right? So say, okay, buffer pool manager, fetch me a page. I want this page in memory. So what's going to do is it's going to try to fetch the page from the hard drive and bring them to the buffer. The key problem is the buffer will always be smaller than the hard drive, at least in our assumption, okay? So the problem is that at some point, buffer is going to be full, right? So then one key design decision is you need to pick some page in the buffer pool. So like in the buffer to evict them back to the hard drive to make place for some other pages and then serve the upper layer. So, and we talk about different ways to do it. We talk about the theoretical optimal way, if you magically know about the future, okay? And we also talk about what would you do in practice, right? You can do LRU, you can do MRU, right? They have different trade-offs, right? So they work for different access patterns. And above that, right? So everyone just have an illusion that whatever information I want to access will always be in memory. It's time for us to manipulate information. And there's one layer called access method, to really give you a way to essentially access information in your relation. For example, I say, okay, so I want to screenshot scan my relation. So that is actually one access method. But you can access information in different ways. For example, you can build a B tree index or B plus tree index over your relation. And then you can provide a kind of access method to say, okay, I want to do index scan, right? I want to scan the leaf node of my B tree. And then I want to, for each one of those key, right, I fetch the tuple. Right? It's going to be very slow because a whole bunch of random access, right? But you can do that. You can say, okay, I can look up my index, right? So I want to do index scan for the key between 5 and 6, something like that, right? Then you can actually traverse the B tree, find the right key, fetch the tuple, okay? There's two different type of B tree we talk about. There's a clustered B tree, there's unclustered B tree, right? Go back to textbook and you will see the difference. And we talk about hash table, right? So that's another access method you could have. You could build a hash table, then you can look up for the hash key, right? So what's the interface of this to the upper layer, right? It essentially gives you a higher level abstraction to access information without talking to the buffer, right? Whenever you are implementing the operator execution layer, like say, I implementing next loop join, right? I can just directly use all those access methods without talking to the buffer. That is the fundamental goal, okay? And then there's the operator execution layer, okay? So here our goal is really try to implement all the relational algebra operators that we have been talking about in the first half of the course. How to do join, how to do projection, how to do selection. So what's the interesting part of this? The interesting part is for each of this operator, right? You can have different ways to implement them. Right, just as one example, for join, we talk about a whole bunch of things. You can do next loop join, right? You can do block next loop join, right? You do that block wise. You can do hash join, you can do sort merge join, right? So the whole bunch of things you can do for every single operator. But in this layer, you provide all of the implementation and you provide a cost model, okay? So and then the upper layer, the query optimization layer, can actually, according to the SQL query, pick the best implementation of this operator. But this is the layer you actually implement each of those operators. So the interface to the upper layer is really, yeah. So you give me two relations, you give me relational algebra, that operator, I can run them. Okay, so it's an even higher level abstraction to access information in a table. So, and what it's going to do is not going to implement this by talking to the buffer. It's going to implement all of these operators by using the access method that the system provides. Okay. And then there's the top layer, which is your query optimizer, right? So in this part, it's really the place that the system put everything together. You give me a SQL query. What I'm going to do, I'm going to translate that into a logical model. Okay, so I think everyone just that should be familiar with that term now, right? What's a logical model, right? So that's a machine readable representation of your SQL query. Okay, and then what the query optimizer going to do is going to translate that into a physical plan, which logically gives you the same result, but could be faster to run. Okay, and a physical plan is a tree or DAG of relational algebra operators. Okay, and each operator is implemented in the lower layer. Okay, and then we talk about different execution models, right? About how to run it. We talk about the volcano model, the iterator model. We talk about the block model, motorization model, right? So, and then the query optimizer part is going to have a cost model, right? To do kinetic estimation, to instantiate all the constant in the cost model, right? And then have some search algorithm to actually search this extremely large search space to find the best kind of execution plan given the SQL query and run it. So that's what's going to happen in this layer. So the query optimizer will not will not just access the buffer, right? It actually will not access the access method layer, right? It's going to directly use all the relational algebra operators that you have been implemented. Okay, so it will not interact with the other lower layers. So in the exam, right? So like how would you test your understanding of this, right? So essentially, the skill we really want you to grasp, like in this part, is first one, and we really want you to understand how a simple database works, right? Because then when you write a SQL query, you can have some reflection about whether you are giving the system a SQL query that it has a chance to succeed, right? In the sense that it could be fast, right? So the skill is try to understand how simple database work. And then we talk about a whole bunch of concepts, and we can expect you to understand all of them, right? So what is the performance model of a hard drive, right? What is seek time? What is transfer time, right? So what is a disk manager, right? What is storage layout? How does information being organized in my database? Different strategies of buffer management, that's very important, right? And also different access method, right? What is sequential scan? What is the cost model of sequential scan, right? What is B plus tree? These two different type of B plus trees, right? And what is the cost model of B plus tree? What is the hash table, right? So, and also whole bunch of like operators, right? Whenever you are doing the scan operator, when you are doing the join operator, all those different implementations of those operators. Next loop join, intent next loop join, what is their performance model, right? How can you reason about their performance? Hash join, right? External sort, all those operators, different implementation we talk about in the course, right? So we expect you to be able to say, okay, this is the join. This is all the different ways to implement the join that we talk about. For each of them, given the current assumption, what is the performance? How many I/O do we need? Okay, so that is something that we expect you to know. And also query optimizer, what is iterator model, right? Giving a query plan, right? How does the whole thing get executed, right? So what are those query writing rules, right? How to generate kind of a new plan that is has a equivalent semantic, but potentially different performance. How to do cardinality estimation, right? How to instantiate the constant in the cost in this very simple cost model. How to do cost-based optimization, that's how to search within that space, right? So that's huge dynamic programming, like problem that we talk about. So all of it is a larger amount of concepts, right? But also we spend like 20% of the whole course talk about these components, right? So we expect you to know all of them, okay? Especially the cost model. Okay, I know it's a lot, but this is also a very significant part of the course. So in the exam, surprisingly, we don't have one question for this. I think this year it will be very similar because it's very easy to test, right? About system. That is, we can actually ask you to reason about the end-to-end behavior of the system, right? And you need to know all the layers to be able to do it, right? So essentially, right? So this is one example question from previous year, right? Essentially, it could be we give you two relations, R and S, and give you a whole bunch of assumptions, right? For example, R have this many tuples, right? And each tuple has certain size. And we say, okay, page size is 1 megabyte, right? So from this, what can you get? You know how many pages you have, right? And then you, yeah, and then you actually know how large each relations are, right? And then we give you some assumptions on the hardware, right? For example, we say, okay, so all the information are being stored on hard drive, right? Here's the seek and rotate time, right? So for each random access, you pay 20 milliseconds, and we have the bandwidth that essentially every single second will transfer the data. You can transfer 256 megabyte, which is very fast disk, to be honest, right? And then, yeah, so that's your assumption, okay? And then we say, okay, so here is a SQL query, like Q1, right? I just join two relation, right? A natural join on the ID column, right? And then I do another selection on R. And then we give you a query plan, for example, something looks like this. This is your query plan. As you can see, right? So you need to understand what the query, how to read the query plan, right? So we are doing iterator model, right? So essentially, it's a volcano model, right? So like essentially like each operator going to call next, right? And then call the next of this operator and call next of here, right? So here, like you first do a sequential scan, you first do a selection on R, right? And then you join that with S. And then you do the projection. Okay, so very simple query plan. And then we give you, for example, the constant. Here you say, okay, so we magically we know the cardinality of the selection. Okay, so that is something from the optimizer, right? So you need to know what cardinality is, right? And what's the role of this selectivity kind of value, right? And how to plug it into the cost model, right? So, but we give you all the assumptions. Okay, we tell you, okay, so this is cardinality, right? We also give you actually more assumptions about the index, right? So here is actually whenever you are accessing the index, right? So this is our assumption to make sure everyone is on the same page, right? On the cost model. We will try our best to give you all the assumptions, right? And also make sure whenever there's ambiguity, right? I mean, for example, if you do sequential scan, probably no ambiguity, we will not give you that, right? But when there's an index, right? So this is actually our assumption about how many pages you are going to access using the index. So, and then given this, we can start to reason about the behavior of the system, right? And then there's could be different type of questions, right? And this is just one example, right? And we might change like which behavior we are curious about, right? So this year, but so here's just one example, right? So for example, if you just like think about the selection, like this operator, right? In the query plan, right? So assuming there's an index on R on the same column that you are querying about, right? You can either do index-based access or can do a table scan, right? And there's just two different ways for to implement this operator, right? And maybe we ask you to calculate how much time it would take, right? To perform selection, this operator using each method, right? So here's very simple, right? For each different ways of implementing this relational algebra operator, we talk about the cost model, right? So I think lecture, yeah. So like in the middle of the course, we talk about cost model, right? And once you understand the kind of the cardinality of selection, right? You kind of know how to plug them in, right? So, and you can calculate them, and then you can actually compare them to see which one you will do in this scenario for this operator, right? So this kind of very, very natural, and it's not that hard once you understand how the system actually works. Yeah, and we can do more, right? For example, we can say, yeah, so now let's think about the join, right? So here's the join operator, right? So this operator. So let's think about the join, right? So yeah, I mean, you can they have two different ways to deal with the join, right? You can do next loop join, right? You can do hash join, right? So then let's try to calculate here how many comparison you are going to do for a next loop join, how many hash table access that you have when you do hash join, right? So in this case, it's kind of very simple, right? So let's take the hash join, for example. How many access do you have on the hash table when you do hash join, right? What do you need to do, right? I mean, you have the relation on the left-hand side, you have relation on the right-hand side. You first build the hash table, right? You scan one relation. For each tuple, you put them into the hash table. You have one access to the hash table. And then for every single tuple on the right-hand side, right? You need to probe the hash table, right? If there's a match, you output, otherwise you're done, right? Otherwise you move on to the next tuple, right? So essentially the thing that you need is the number of tuples on the left-hand side plus the number of tuples on the right-hand side, right? So that's very natural. And then in this context, how many tuples do you have on the left-hand side, right? So left-hand side come from this selection operator, right? Essentially the number of results you have in the selection operator plus the number of tuples you have on the right-hand side, which is S, right? So essentially here, right, the number of hash table access is equals to this, right? The cardinality from left-hand side plus the size of the right-hand side, right? And then we gave you the assumption, you know the cardinality, right? So then it's done, right? So yeah, so I mean, it's not that complex, right? So once you understand how the system actually works, right? So yeah, so there's a whole bunch of things we can do, right? Assuming you are doing next loop join, right? Then we can reason about the join order, right? Because if you think about query optimization, right, we actually focus like large amount of our effort on kind of optimize the join order, right? Like which relation should be the inner relation, which relation should be the outer relation, right? And then there's different considerations given different buffer size, right? So assuming you want to minimize the usage of your memory buffer, right? So in this case, you might want to have the smaller relation, right? So as the inner relation because it's smaller, right? In the best case, you can actually cache it. In this case, kind of try to reason about this and try to tell us, in this case, under this assumption, right? Under this objective, this is the query plan that I would have. I would put, for example, the smaller one as inner relation. I will put the larger one as the outer relation in the next loop join. Yeah, so this is actually some example questions about on the system side, right? So as you can see, it's not that many questions, but every single question essentially require you to have the understanding of the whole stack, right? Then you can actually answer them. Okay, so this is actually for the query processing part to just set the expectation, right? So it's very important for you to understand the cost model. It's really, really important. It's very, very important for you to understand different ways for you to implement the same thing. And it's very important for you to understand when you're doing query optimization, what are different factors that are going to have effect, have impact on the performance, and how to reason about it. And that's very important, okay? And also try to understand what each layer is doing, because otherwise you may have a hard time to just parse the question, okay? For example, what cardinality is, right? So like try to make sure you understand how does the system put everything together in that 5 different layers, okay? And then in the last chunk of this course, we kind of switch gear and talk about something different. So we start by this motivating example about the potential problems that you could have when you have multiple SQL queries or multiple groups of SQL queries running together, but you do not control their correctness, right? So in this case, right, we talk about the kind of the blockchain example, right? Someone just keep issuing thousands of those kind of SQL queries. At the end of the day, they get more money than they have, right? So it actually bankrupted the whole kind of blockchain exchange, right? So a couple of years ago. So essentially, we want to introduce the abstraction that say, okay, so this is a group of instructions, and here we are going to call them a transaction. And then if you do give me a group of instructions, during the execution, I'm going to give you some type of guarantees of correctness. And we talk about 4 of these guarantees, right? So there's atomicity, there's a consistency, there's isolation, there's durability. The game here is you give me a group, I try to automatically enforce all of these 4 properties during my execution to make sure whenever you are building your application using transaction, you can always assume all these properties are satisfied. So that is the contract the system trying to give to the user. So what's the formal definition of transaction, right? So here we think about database as a set of objects, okay? So and each transaction is a sequence of read and write operations. So here's like you can read one object from the hard drive to in-memory variable, right? You can write something back, okay? And whenever we are talking about essentially isolation, right? We always assume whenever you write, the change is reflected inside database, okay? later we talk about recovery, like we talk about different things, but this assumption will be made clear in the question, whether write is going to be reflected immediately or not. Okay, so and the new transaction begins with like start with begin, right, but can end in two different ways. You can either commit, which means that you want all the changes to be saved, to be reflected to your database, or you can abort, right? Which is say, okay, I have a transaction during the execution, I don't want to do it anymore, right? You abort and you undo all the changes. The abort can be initiated by the user. User can just say abort, or can be done by the database, right? So now you should know some scenarios, right? For example, you are doing two-phase locking, there's a deadlock, right? You need to abort some transaction to free up the deadlock. Okay, so in that case, the system may issue abort, or maybe during execution, someone put the plug of the machine, right? So in that case, yeah, I mean, essentially like the nature kind of issue abort, right? So here's just one example. You have two transactions, you have read and write like this. You have some integrity constraint, then you can define consistency, right? So first, both transactions are consistent. They bring database from one consistent state to another consistent state. One important concept is something called schedule, right? So there are just different ways for you to mix instructions together. Every single different ways is a schedule. There are some schedules that serial schedule, right? That means that you run the instruction of one transaction first, then you run the other one. There are two serial schedules. We will have two transactions, okay? And you can just do the exercise to follow them step by step, right? So this is our assumption, right? It's going to bring your database from state, for example, 1010 to 220, 220, okay? And there are two different serial schedules, right? But there are other schedules that are not serial, right? So, and then we define the notion of serializable schedule, right? Which is essentially, that's all the schedules that are going to give the same answer as some of the serial schedules, okay? So for example, you can run the first instruction of T1 first, you run the first three instructions from T2, so on and so forth, right? If you read about their behavior at the end of the day, right, you get the same result as some serial schedules. Okay, we don't care which serial schedule, some serial schedule is the same, then it's fine, the whole thing is serializable, right? So and the game is really, how can you enforce serializability when we talk about isolation? How can you make sure whatever schedule your database system allows is going to be serializable? That's the game, okay? That's the isolation part. And we talked about essentially two different ways for you to do it, right? So there's the kind of optimistic way and there's a pessimistic way, right? So when you're dealing with this whole thing in a pessimistic way, you're actually assuming if you do nothing, there's a whole bunch of conflicts going to happen. In that case, I need to prevent conflict from happening, okay? So essentially, before you can do anything, you need to hold a lock of the information, right? And we also talk about the optimistic way of doing this, right? We assume, I mean, most of the transaction, maybe one scenario, most of the transaction are read only, right? Maybe every week you have one transaction write it, right? So then in that case, right, even if you do nothing, conflict is going to be very rare. And then I can try to have, say, all the transactions that do whatever they want, but before you commit, you check with me. And if you kind of trigger some conflicts, I'm going to abort you. Otherwise, I'm going to allow you to commit. So this gives you two very different ways to enforce isolation, right? One is via locking, another is via, for example, timestamp or snapshot isolation, right? If you do PostgreSQL, right? So I think that the default version is some version of the snapshot isolation thing that we talk about in the course, okay? When we do MySQL, right? So the default is actually using locking. So now let's take a break. When we get back, we continue this, right? If you have any questions, I'll be here to answer. Yeah. Yeah, in the meantime, I'll try to fix the link. Yeah. Okay, so let's continue. Yeah. So I think there's like about slides, right? So there's some problem, I think, probably on the OneDrive side. So I update the website. So I put everything in Dropbox, have another link, right? So I think that one should work fine. Okay. If that still have problem, let me know. Okay. And tomorrow, if the OneDrive still have problem, I will put the slide somewhere. Okay. Yeah, but right now you can just open the Dropbox link on the website, and then you have the identical copy of the slides. Okay. Cool. Yeah, we talk about isolation, right? So how can you make sure whenever you have multiple transactions running at the same time, that the database only allow a schedule that is serializable, actually conflict serializable, right? So, and then there are two other properties, right? For example, atomicity and durability, right? We also talk about them. So what is atomicity, right? Also, what is durability? Let's talk about this one for easier, right? So it just means if system crashes after a transaction commit, so all the effect of transaction will not get lost. So they will remain in a database. So essentially, right, you have a transaction, right? And as long as the system tell you it commit, and even if the system crashes at this point, durability means that all the effect, all the changes conducted by the transaction will be there. Okay, so the crash include actually the system crash, or it also means that other transactions cannot undo a transaction that's already committed. Okay, so you cannot have those cascading abort effect for committed transaction in this scenario. So that's durability. Whenever I commit, the change is there. I will not try to undo a committed changes. Doesn't matter whether nature trigger it or whether adversary party trigger it or other transaction trigger it. I will not allow them to do that. So atomicity actually deal with the system failure or system crash at a different point during execution. It actually means that each transaction, the changes, like it's either all the changes are in or none of the changes are in. Okay, you will never have a database state that is halfway done. Whenever you recover from failure, right, you will not say, okay, this transaction, like the first 50% of changes are in, the last 50% are not in. You will not have something like this. So different from durability, which cares about system failure after commit, atomicity actually cares about system failure during the execution. So for example, what if the system crashes at this point? It's finished running SQL 1, but haven't finished running SQL 2. When you recover the system from the failure, right? Atomicity means that all the changes done by SQL 1 going to be undone because I haven't run SQL 2 yet, right? So SQL 1's effect cannot be in database if I recover from the failure. Or if you crash at this point, right? It means that the database could be in two states. Both are fine, but it can only be in one of these two states. Either both changes are in, because I'm just maybe right before commit, you crash. I kind of know I'm about to commit. When you recover, I recover it, right? Or none of the changes are in. I just undo everything. Okay, I will never have something in the middle. Okay, so that is atomicity. So this actually go into the theory of recoverability because not all the schedule are easy to enforce durability and atomicity. And we talk a little bit about the theory here, right? So if you have a schedule, you have two transactions, T1 and T2, right? So we say T1 read from T2, right? If T1 read a value written by T2, at the time T2 was not aborted. And then we define these three different family of schedules. So there's a recoverable schedule, right? Have this property. If Ti read from Tj and commits, then that implies essentially the commit time of Tj is earlier than the commit time of Ti, right? So there is the second family of schedules called avoid cascading abort, right? Which means that if Ti read one object X from Tj, right? So then you must have the transaction J commit before the read time. Okay, and then you have the strict schedule, right? Just extend the void cascading about ACA schedule to both read and write. Okay, so for each family of these schedules, you have different property of recoverability. For example, if you think about recoverable schedule, right, it means that you can enforce durability, because if your schedule is recoverable, it means that you do not need to undo a committed transaction. So here's just one example, right? So here, right, in this example, T1 read from T2, right? Because the read happened after write, and at the time of T1 reading it, T2 hasn't aborted, right? So, hadn't committed, right? Either way. And then if you compare the commit time, right, you can say, yeah, so T2 need to commit before T1, right? So that's the definition of this family of schedules. If that is true, it's recoverable, right? So as you can see, right, so because before T1 commit, T2 must already committed, right? So T2 will not trigger the abort of T1, okay? So that is a high level idea. So what if you don't have this, right? If you have the other way around, if you have T1 read from T2, however, T1 commit before T2, right? In this case, what could be the problem? The problem is after T1 commit, what if the system crashes here, right? What if you need to undo T2, right? In this case, you also need to undo T1, right? So that means that if the schedule is actually not recoverable, it's very hard. It's very challenging, if not impossible at all, to enforce durability. Okay, so that's why we always want schedule to be recoverable if you really want durability. Right? And then there are different families, right? So there's another family called ACA, right? So which essentially means that if TI read from TJ, right, then TJ must commit before you read it, right? So this is actually just try to avoid cascading abort, right? So like assuming in this case, right, so T1 read from T2, but T2 also commit before the read, right? So it's an ACA, right? Otherwise, what would happen, right? T1 read from T2, but T2 commit after T1, right? If the system crashes at this point, as you'll see, I also need to abort T2 because system crashes. But on the other hand, I also need to abort T1, right? Because T1 is reading from T2, right? If T2 doesn't exist, then the value that T1 read is not valid anymore, right? So if you have a schedule that's not in ACA, you are going to have the cascading abort behavior, which is not something we want. So when we talk about strict schedule, right, so which is very similar, just extend ACA to both read and write, right? So if you think about this, right, if you put them together, right, so in the core, there's all those serial schedules, which is recoverable and also serializable, right? And then you have one dimension about recoverability. So there's strict schedule, ACA, recoverable, and all the possible schedules. On the other hand, right, so there's the serializable schedule, right, from the isolation side. This is like two orthogonal dimensions in trying to classify schedule, right, according to their properties. And when you are building a database system, right, so at least the default behavior is you want something here in the green region, right? So that you want something that's serializable to enforce isolation, and you also want something that's strict, right, to enforce atomicity and durability. So how can you do that, right? So we talk about a very simple schedule, like very simple mechanism to do that using locking, right? That's called strict two-phase locking, right? Which is essentially when before you read and write on certain object, you need to like own the lock, like on that, hold the lock on it. But you cannot just like acquire lock and release lock in whatever way you want, right? So essentially you can you partition the transaction into two different phases, right? In phase one, that's a growing phase, you can acquire locks, right? But you cannot release lock. In the second phase, you just keep all the lock until the end of the transaction, and then you release lock at the end of the transaction. So it's very easy to see that if you have a strict two-phase locking, this mechanism, it's going to give you isolation, but also going to enforce the schedule to be strict. Okay, so the proof idea is very simple, right? So essentially, you're only holding log until commit and abort. It means that if T1 read from T2, T1 can only do that after T2 commit or abort. Otherwise, it will not have the log. Okay. So given this, right? Given this way of enforcing a schedule that's strict, let's talk about how to recover from failure. Okay. If schedule is not strict, then it's very hard to do it. So we talk about different ways to recover from failure. And the high-level idea is by using logging, right? Before you commit, you want to keep a log to make sure even if the system crashes anywhere, right, during the execution, you can still read the log and recover from it. So we talk about different ways of essentially the key, there are two fundamental questions here. Right, one fundamental question is what information do you want to put into the log file, right? And second is when do you want to flash the log, and when can I tell the user that you can commit? So about the first question, right, we talk about different things. You can do something called undo login, right? You put the old value, right? You can have the redo login, you put the new value. You can have something called undo redo login, right? Which you put both the old value and the new value for your updates. And then given different type of logs, you have different protocol about when are you allowed to tell the user you can commit, and when do you flash the log, when do you flash kind of the actual changes to the hard drive. So the best way to learn about this is in the textbook, there's a very clean example about what actually happened inside the system. I hope I have a better way to teach you that, but the best way is just read that chapter, go through the example and step by step. Okay, like we have been doing two of this example in the course, right? So we are not going to do that again today, right? But go through that one by one and try to think, okay, at this time point, this is what happened, that makes sense, this is what's in memory, this is what's on disk, and think about why they try to enforce the protocol like that. Okay, once you understand this, it's actually not that hard, okay? Yeah, and also in terms of the exam, right, about transactions, right? So what is our expectation, right? So why are we teaching you this? So the skill we really want you to have is, first one, understand what is the four properties we want from a transaction, okay? What is atomicity, what is consistency, what's isolation, what's durability. It's going to be very important because when you really build a real database application, when you go to a job market, right? So you want to be able to reason about the contract you have with the database system, right? Whenever I give you a transaction, this is what you are guaranteed for me. Then I can build the correct application, right? So understand what is isolation, understand what is serializability, and what is conflict serializability. What's the difference, right? And also how to enforce isolation using two-phase lock-in, right? And strict two-phase lock-in, snapshot isolation, right? And also for atomicity and durability, you understand recoverability, right? And how to enforce it using login. And also what's the relationship between recoverability and isolation, right? And how does strict two-phase lock-in provide you a way to do both. And also all the concepts, right? What is serializability? Right? So I think everyone should understand. What is conflict serializability, what's the difference, and how to check conflict serializability, right? We talk about all those very cute graphs, right? You can see whether there's a looping dependency graph, right? So what is the protocol, the mechanism of two-phase lock-in? What is the mechanism of strict two-phase lock-in? What is snapshot isolation, right? So what is different like family of schedules in terms of recoverability, how to do undo login, how to do redo login, how to undo redo login, right? And also the fact that strict two-phase lock-in is both can both give you isolation and strictness, right? So if you understand this, I think you will find all the question to be actually very simple. Okay, so this is just one example. It's actually not that hard, right? So we could give you a transaction, right? So so here's, for example, BI is the beginning of one transaction. Here's read, here's write, right? Here's commit, here's abort, right? And in this example, we will make sure whenever we talk about write, we tell you whether it's going to be reflected on the hard drive immediately, right, or not. But in general, right, so if you do not see output here, then of course it's going to be reflected, right? So if you talk about isolation, right, serializability, it's always reflected. Whenever you talk about recoverability, probably not, but we'll make that clear this year, okay? So, and then like one thing is, okay, so we could give you some schedules. For example, if you look at here, this is one schedule, right? So first, transaction 1 read A, then transaction 2 read A, transaction 1 write, then transaction 1 commit, transaction 2 write, transaction 2 commit. Yeah, I mean, I'm scheduled like this, right? We may say, okay, so are they serializable? Right? So yeah, then you can check it, right? You can check conflict serializability, right? And then if they are conflict serializable, right? So you give us a kind of serial order, right? So it's not that hard, okay? And then the question is, okay, so we have a schedule, right? What is their property, right? Which, for example, recoverability family they falls into, right? For example, if you look at the first one, right, this one has very good properties, this one actually strict, right? Maybe the second one is recoverable, right? What is the strongest recoverability class that you can claim about this schedule, right? And whether you can actually enforce it using strict two-phase locking, right? For example, in strict two-phase locking, is this schedule possible? Or in snapshot isolation, right? Is this schedule possible? Right? You just need to understand the mechanism of different ways to enforce isolation, then you can reason about it, right? So as you can see, right, the fundamental thing we want you to get is what is reliability, what is recoverability, how to check it, and also how to enforce it. Okay, if you understand this, yeah, I think you will be fine. Okay, so this is actually all the content for today, and this is actually the last lecture of the whole semester, right, for database, right? So we talk about how to use database as a user, how to try to open the box a little bit, right, about how database actually works. I hope you guys had fun. I hope you guys found database interesting and something you would continue to learn, right? And also thank you guys for all your attention, all the feedback you gave us. I'm sure next year we will do even better job, right, in running the course to make sure your colleague or your future colleague can have an even better database course, right? So yeah, so I think that's all for today, right? So I think during the summer during the summer break, we have 4 additional office hours. Just call in, I'll be there, I've recorded and uploaded, right? Otherwise, have fun. If you have any question, comments, questions, feedback, concerns, just let me know. Okay, just send me an email. I'm happy to jump on a call to listen to your concerns and how we can do better. Okay, so that's all for today. Actually, for the whole semester, I'll be here to answer your question. But otherwise, good luck in your exam. Okay, so if there's no questions, I'll see some of you in the office hour. Okay. Cool. Yeah. See you guys. Bye.